Okay, so what I'd like to talk about today is I'd like to spend today talking about, an assortment of machine learning algorithms. This is Chapter 11 is on machine learning. I'm going to we've spoken about a couple of things. We've obviously spoken about regression and logistic regression in a fair amount of detail. There are a tremendous number of different machine learning algorithms out there. So if you take a look at machine learning, there's, you go to a machine learning book, there's a list of a dozen different ways that you can do it. A lot of these machine learning algorithms are what I consider to be clever in that they have some surface appeal when you start to talk about what they're actually doing, okay? And so I think that's good. But it's not always 100% clear why there are so many different machine learning algorithms, okay, or which one is best in a particular application. That's why I kind of call it a zoo. There's kind of a lot of different animals running around, and it's hard to know why you should care about one more than the other. And if I want to compare different machine learning methods, the dimensions that I would kind of identify are, one, there's this notion of power or expressibility, which would govern something about how complicated a model could it possibly learn, okay? And in principle, to be able to recognize and distinguish between different data sets, the more power you have, the more expressibility, in theory, the better off you are. There's this notion of interpretability. If I give you a model, can you make any sense of why it is making its decisions, which I personally think is an important thing for helping to debug models. There is what I would call ease of use thing. Different machine learning methods have different degrees of parameters and knobs to twist. And so if you are good at using a particular machine learning algorithm, you know how to twist the knobs, but often people are using them relatively out of the box. And so the question is, you would like one that is relatively easy to use in general. There is a trade-off of training speed. How much does it have to analyze your data to make a model? And then prediction speed. If you're going to be using something to classify large numbers of examples, okay, the speed at which it makes a... So if you have a huge data set, training speed might matter because it may take you months to build your model. If you have a model that's going to be called very, very often, prediction speed is important. I would say that the classic example of prediction speed being important are these models that are used in high-frequency trading on Wall Street, where they have these, you have these computers that are making buy-sell trading decisions, and the way they work is largely by being faster than other people, so they do crazy things like locate the computers as close as possible to the trading floor itself so they don't have to spend the electronic delays shipping signals around. And so here, being able to make a prediction, should we buy or sell this thing quickly, makes a difference if you can do it faster than other people. Okay, so sometimes prediction speed is important, sometimes training speed is important, sometimes neither of them matter, and different machine learning methods have different trade-offs between them. Okay, any questions about that? That should be obvious. So when I was writing the book, I asked a bunch of people who I considered to be knowledgeable, okay, to compare a bunch of different machine learning methods on each of these dimensions. And of course I got a certain flack from them because they didn't, I said 1 to 10, 10 is best, okay? And of course they kvetched about certain things. But this is kind of what, when I normalized it and did what I wanted to do with it, this is what I came up with. And so if you look at sort of the methods we've studied now, linear regression scores very well on just about all these methods. It tends to be weakest on power of expression. Because again, all linear regression can really do is form a linear model. Okay, it assigns weights to features and basically adds them up. Okay, nearest neighbor, which is what we talked about before, has the property that I guess for training speed it is best because it doesn't do any training, okay? But generally speaking, in performance, it's typically relatively easy to use, okay? The prediction speed is slow, the training speed is fast, okay? Any questions? I might have, when I was scoring, I'd probably score linear, nearest neighbor is easier to use than linear regression, but I had to accept votes. Any questions? So today we're going to look at some other methods. We're going to look primarily at decision trees and boosting, okay, and maybe a little bit at support vector machines, okay? And when I look at these ratings, what stands out to you about these different methods? How many people have heard of decision trees? How many people have heard of support vector machines? How many people have heard of boosting? So some people have heard of all of these things. What stands out to you when you look at these numbers, especially in the middle of the chart? Yeah? In general, okay, so one observation that is interesting is as we go to the more advanced methods, power of expression generally goes up. We're going to be learning about, learning models that are potentially not linear models, okay? And so that gives us more ability to express models. So that's certainly right. Generally speaking, as you work harder for this, other things get worse. That's kind of what you're saying. Yeah. By power of expression, I mean how complicated a model can you develop, okay? So if you think about it, a model is going to, you take input data, you produce a model to make decisions, okay? Is this going to be classified in class 1 or class 2, okay? There's a question of mathematically how complicated a model is it, how rich a model is it, okay? Linear regression basically just supported linear weights of features. It was an additive sum of features, okay? And, these other models like deep learning can have millions and millions of parameters in wildly nonlinear ways. You can build much more complicated models that way, okay? They generally, as the models get more complicated, they get harder to understand, and they are harder to build. Okay, which probably would not surprise anyone. Any questions? The other thing that I would say when I look at this is that there's this vast sea of methods in the middle that don't really stand out in any particular way. Okay, so there's kind of a whole zoo of methods, and in my mind it's a little hard sometimes to see which is best among many of these kind of things.
Overall, they don't have any low scopes, they don't have any 3 or 4 anywhere. Like overall, in the performance, these are all like good. For typical model, you see that there are some 3s and 4s, and for the small also there are some 5s, something like that.
So,
but they are like good overall. Like
so what I would say is the most advanced. I think what you're saying is the most advanced methods, the ones that give the richest models, give you the most freedom to hang yourself. That is kind of what you're telling me, and that is a general rule of life. Okay. Any questions? Okay, so what did I notice when I did it? First of all, linear and logistic regression is generally nothing to be ashamed of, okay? If it, the problem is that models, it can only build these linear models, okay? And often for many things that is good enough, okay? So that's one other thing. There is no single method that dominates all the others in everything, okay? And to my mind, the advantages of most of these methods are relatively murky. That doesn't mean that one can't do better than what you're doing on your own data. It doesn't mean that they're not all interesting to learn about, okay? But there is a theorem that they say, which is, to some degree of formality, but it has a great name called the no free lunch theorem, that can prove that there's no single machine learning method which will work best on all problems, okay? Some people take this as a moral that therefore you should try all methods on your problem. And generally speaking, I think that most methods often they perform very similarly, and the differences are probably more likely to be variance than they are really deep insight. Okay? But what is true is that all of these methods have some people who swear by them. And so, to a certain extent, I think the ability to make different methods work is a function of experience. And the more experience you have working with a small number of methods, the better off you are at setting up your data for them and stuff like that. Any questions about that? Yeah.
Is it possible that theoretically some model is supposed to be working better than the other model, but then when you actually implement it, then you see that the other one is giving you better results than the first one?
Okay. So, first of all, there is no, if we believe the theory of the no free lunch theorem, there is no method that is guaranteed to be best in all cases. Okay? So no, there would be no theory that would state that. You mentioned something about implement these. For most of these, again, you live in a world of packages and libraries. And in general, even though these algorithms are kind of neat, and I'm going to kind of explain how some of them work, most of them are probably not things that you really want to be implementing from scratch. Okay, these are things that most of these are, for the most part, methods that have good implementations, and you're probably better off using somebody else's implementation than writing it. Yeah. So, generally what typically happens in my mind, when I see students do it, some students will proudly say, look at me, I ran them on all these different, my data on all of these methods, and they will proudly show that the performance on all of them is almost the same. But they'll be very excited that one was, instead of being 68% accurate, was 69% accurate. And they'll proudly circle that as saying that that's the best one. Most likely that is a question of variance and overfitting rather than some insight of the method. Any questions? That's my opinion on these things. Anyway, any questions?
So like if the difference is more than 1%, suppose the difference is 5%, will you say the same?
Well, you have to decide a little bit what level of difference you think about. So let's think about it. First of all, would you want to take the lower scoring, less accurate method over the one that did more accurately? Part of me says it's a function of the complexity of the model. If I have a relatively simple model, like linear regression, that is doing the same as some very, very complicated model, okay, or almost the same, my money would probably be on the lower, the simpler model, kind of an Occam's razor idea, right? If you have a model with fewer parameters and fewer degrees of freedom out there, if it's doing almost as well as the more complicated models, I would ask myself, is the more complicated model likely to be overfitting, or is it likely to be insight? Okay, that would be one question. So these are the kind of things you should be worrying about. Is there a hard and fast rule for how you would pick this? The answer is no. But generally speaking, I expect several people in here are going to try to run it on, because it's easy in Python to run their thing on many different learning methods. And I expect you to fully find out that they're about the same. And I fully expect you to overinterpret the small differences. Any questions? Okay? That's generally thing. But I do think it's interesting to understand what these methods are and why they might be different. And in particular, like I'd say, the notion of expressibility is probably the biggest single thing to understand here. So we are used to linear classifiers like linear regression or logistic regression, where we would try to put a single line through our space. Here we've got two different points. Let's say there are the orange-colored points and the blue-colored points. Okay? Recognize that if we had a world where our data had a more complicated property to it, like the exclusive OR, okay, we couldn't fit it using a linear classifier. So let's think about it. Suppose, let's say, just to view the picture a little bit, let's say that the points are in two colors. They are blue points and orange points, okay, and they are colored by here, okay, and they're both points in the XY plane. Is there a single line that would separate these two? Okay, it should be pretty clear that no matter where you draw the line here, there is no way to partition orange from blue. Nonetheless, there is a pretty clear function that would separate it. Okay, if x is positive, okay, and y is negative, or x is negative and y is positive, then we have got a classifier. Does everybody see that? And so kind of the exclusive OR is the poster child of a function where there is a simple classifier for it, but you would never see it if you lived in linear regression world. Does everybody see that idea? Now, in nearest neighbor world, would you see it? Yeah, kind of. Okay, so nearest neighbor did not develop this kind of, right. If these were my training points, I would be partitioning, I'd have some rough times at the corner, probably my line wouldn't be straight, but it would be able to recognize something like that. Okay, but what you call it? But linear classifiers can't do the job. Any questions? So this is what I mean by the sort of power or expressibility. You want, ideally, if you think your data has some complicated structure in it, you want to make sure your models can support that structure. Okay, and exclusive OR is the poster child of something that seems simple but isn't. Okay, any questions about that? Can anybody think of a function, though, that is like an exclusive OR? Can anybody think of a set of classes where you would be able to recognize it and it would have the property of being an exclusive OR? Okay, so think of something in the world where you would make a judgment based on the exclusive OR of two variables. Okay. Okay. Can you think of some classes on things that would be, on two variables that would satisfy this kind of a structure? Okay. I want someone to suggest something that's wrong, at least. Okay. Any kind of property in the world that classification of things that you might be? What? A coin toss? I don't quite know what that means. Again, typically here for exclusive OR, we need two variables going in, right? And we want it to be the case that, something's in a class if either one of them is high. Okay? We might say somebody is large if they are tall or they are heavy. Does everybody see that? But is that an exclusive OR? No, because here you've got all the people who are tall, and here you got all the people that are heavy. This is, it's still not really a linear classifier somehow, although maybe you might imagine carving out something like this. This might be what would separate the light people from the heavy people, right? Anybody think of any example that is an exclusive OR? Okay? It's not as easy, but these things do come up. And I think the example that I came up with, the best example was, suppose we wanted to build a classifier to say whether somebody was gay or straight. And if I'm missing this in a way that upsets somebody, I apologize in advance. But let's imagine that one of our dimensions was how male or female somebody was by physicalness, okay? And there was some other thing of how much they liked men or women by preference. You can imagine that every person is now a point in gender and preference space. Does everybody see that? And by definition, people who are straight are women who like women and men who like men. People who are straight are women who like women and men who like men. That's what this is, right? Oh, wait, oh, God, wait, oh, wait, no, take that back. You're right. Say that wrong. Okay? So let me see if I can read my, the straight was the red points. The red points were what? Men. These were, that they were men. Oh, I see. You're saying I got the labels wrong here. Okay? It should be clear, right, that if this is, if greater than 0 is maleness, okay, then right, these points were the men who liked men, and these would be the women who liked women. Am I correct? So those would be, I have my labels wrong, my class labels wrong. Does everybody see it? That according to this, the gay people are the red points, and the, the straight people would be the blue points. Does everybody see that? Okay, so my labels are wrong. Somebody mail me that so I can fix this. Okay? But does everybody see that under this kind of case, there would be no single separator, line you could define in, preference, gender, space that would separate them? Is that right? On the other hand, there is a very, very simple tree, a decision tree of height 2 that would be able to do it. Okay? This is what we would call a decision tree, and that's what I'm going to talk about for a lot of today, are these decision trees. But what would you do if you compared the feature? Is, let's say gender greater than 0? If yes, is preference greater than 0? If so, they are gay. If not, they are straight. If gender is less than 0 and preference is greater than 0, then they are straight, if not gay. Does everybody see that this two-level decision tree is expressible enough? Decision trees are expressible enough to capture something that we couldn't capture by a linear thing. Any questions? And so that's kind of the thing that governs, when people talk about different machine learning algorithms, as whether one is better than another, usually the algorithm itself is not something that I think of as important. Usually it's a question of the expressibility of the model. Okay, so you're not really comparing typically two different support vector machine models. You're talking about the support vector machine is different support vector machine algorithms. Typically, you've got one package. You've got a model that says, these are the kind of things that I can fit, okay? And the algorithm's job is to, find the best model given that. Yeah. The answer is that the thing about a linear regression deals with lines. It doesn't deal with piecewise lines. That's why we have these other kind of methods. The good thing about linear regression is there is this nice math and this nice way to do it. The bad thing is you're stuck with a line. Okay? Any questions? We'll talk about boosting a little bit later, but you'd like to try to. Anyway, basically, this is why you need to use something other than linear regression. That's the big take-home lesson. Yeah. The orange section would be if I learn this line. This is showing my feeble attempt to try to find the separator by linear regression of these points. I think it was logistic regression. I used logistic regression on these points, and this was the line that logistic regression came up with. Any questions?
And then one more thing, I don't know, how did you measure the x-axis? How do you measure the gender of a person? On the
Well, okay, how do I measure this? Let's say it's a phony example, and that's how I measure it. Okay, that's probably it. Okay? It should be clear that this is a concept that involves an exclusive OR. That much should be clear. It should be clear that I have no idea how to do the measurements or that the measurements are a reasonable thing. Any questions? Okay? Fair enough. Okay, so what I'd like to talk about are these idea of decision tree classifiers, because decision tree classifiers have certain properties that I tend to like a lot. They are relatively explainable. They are apparently, when implemented in their full glory, a very successful method. And they do capture the potential nonlinearities in ways that are relatively simple to understand, but in ways you would never do with linear regression. So what is a decision tree? A decision tree is a rooted tree where every intermediate node is a test, and every leaf is a classification. That's kind of what it is. And basically what a decision tree is, it performs a test typically on one feature, okay, and then asks, okay, does classification by performing the sequence of tests defined as you walk down the tree, okay? So this is a decision tree that was built to decide who survived the Titanic, okay? If you were on the Titanic and you saw it hit an iceberg, if you wanted to know whether you were going to get off the boat, a decision tree like this would have been helpful, okay? If, if were you male? If you were male, then if you were not male, you were female, and the answer was that 73% of the women on the Titanic survived. So this was enough to tell you that that all these people, you would predict that they survived. So what I believe this is going to be that the two numbers that we're going to care about at every leaf are, one, what is the fraction of cases that it describes, and what is the accuracy, the purity, the accuracy of the decision. So if this particular node said that 36% of the Titanic passengers were women, that's kind of the way that I would put it, okay? And of them, 73% of them survived, okay? Now, you could then do, if you were male, you would do a different test. Are you age greater than 9.5? If you were old, okay, if you were a kid, if you were above kid level, forget about it. They didn't let you on the boat, right? On a lifeboat. And of these people, 61% of the men were older than, of the people on the boat were men older than 10, than 9.5, okay? And of these, only 17% of them survived, okay? So we say all of these people are going to die, okay? If you were younger than 10, there was one more refinement that we did here, are the number of siblings that you have a bunch of other siblings, okay? Apparently, if you were young, okay, your elder brothers tried to save you if you had enough kids, okay? And if not, you died, okay? Okay? So what does this show you with this tree? This shows you a fairly small, simple chain of logic that's relatively explainable, okay? It's clear that for every one of your training examples, it covers a particular path through this tree. Is that clear? I give you any example, including the training, or a training example or any other example. There is exactly one path down the tree, okay? We stop refining the tree at some point, okay, once it has got what we would call enough purity to it. Does everybody see that once we have a group of people who the majority of them, a good majority of them survive, perhaps once there's a high enough fraction of them that are in the same class, maybe that's when we stop refining our tree and make a decision for that. Any questions about that? How do we calculate the values here? The values, if this is annotated training data, then the way you would calculate this for a given tree is pretty easy. Once you have the tree, you take all of your examples and run it through the tree. We agree that every one of those training examples is going to end up at one of the leaf nodes. Is that right? So what is this fraction here?
Yes.
The percent is the fraction of total training examples that ended at that leaf node, right? So if we add these things up, what's 36 plus 61 plus 2 plus 2? So that is 100. We ignore the round-off error, okay? You could imagine that in rounding this up and down, that's probably what happened there, okay? But basically, that's going to be the percentage of stuff. That measures, in some sense, how important the node is, right?
And if you multiply this percentage by the fraction and add them, then will it be 1?
Okay, then what we would do is, okay, then there is, the other fraction is a measure of purity. What fraction of these people survived, right? And what you're trying to say, if I multiply the number of things at the node by what fraction of them survived, I would get some measure of the accuracy of my classifier, right? To be precise, since you're calling this person died, you would want to say be multiplying 61% times 1 minus 0.17, right? Because the accuracy, we called this dead, these people all having died, and sure enough, only 17% of them lived, okay? So in this case, what you're really saying is the accuracy of the classifier would be the number of examples at each stage times the fraction of them that we got right, okay? And in this case, it would be 1 minus 0.17, okay, instead of that. Any questions? Yeah? Well, refining the tree would be adding other edges. For example, is it true that, if you notice, we stopped the women's node here. We could have gone further down, right? What if we had added another test there that said, are you a kid, a woman greater than 17? Okay? It could very well be.
We can use only once, right? If we use the parameter age, like once, we cannot use on the other part, right?
No, there's no reason why you can't use, you certainly could use different features on different paths of the tree. And you could even use the same feature on the same tree. Let's say that we wanted to test who was a lively worker. I wanted to try to distinguish who was a lively worker. If a lively worker is anybody who's greater than 18 and less than or equal to 55, which is my age, okay, how would you tell? You would want the test to be, is somebody greater than 18? Yes. If so, are they less than 55? If so, yes, then they're alive, right? Otherwise, they're dead wood or something like that. Does everybody get that? So there's no reason why you wouldn't necessarily want to have the same basic feature tested twice on a path. Okay? It certainly could be the case that you would want to do it.
Like when we train a decision tree,
Yeah.
we measure the variance for each of these features, right? And we choose the feature which has the maximum variance and make it.
Well, how we build this thing we haven't talked about yet, right? Okay? But it should be clear that as far as expressibility goes, certainly it would be a bad thing to not allow you to have multiple tests for the same feature. Does everybody agree with that? Yeah.
So you mean to say that the edges like this age greater than 9.5 being added as the training sample serving process?
So again, the way to interpret this, suppose this tree was given to you, okay? Then how do you interpret it? To classify an example, you're running them down the tree, asking them tests, and depending upon this test, they either go to the left or the right. When you get to a leaf, you take that as your class for the person, for the example. Okay?
We can add the edges also in between. Like in the women's, can we add this age greater than 9.5?
So if you wanted to refine the woman's side, you wouldn't be adding an edge. What you would be doing is replacing this leaf with another internal node. Okay, so instead of it being is sex male, you would imagine deleting this and instead adding a test, is age greater than 11? That's going to give you two possible outcomes, right? And what your hope is, if the purity of those classes becomes more stark, okay, then the better off you are, okay?
So, and how do we decide that?
Okay, so there's questions, how do you build this thing, okay? And that's what we'll talk about in a little bit, okay? Yeah.
Can a node only have two children? Is it like only
Can a node have two children? Again, in general, decision trees are built out of binary tests at each node. You could conceivably have multiple ones, but if you have more than two, you can get the effect of more than two by having a cascade of binary ones, right? You could collapse these three tests into something that gave you four possible outcomes, right? So you can, as far as expressibility goes, binary is good enough. Any other questions before we think a little bit more about these things? Okay? So basically, what does it kind of tell us? Our goal is, when we're building it, we want our leaf nodes to be relatively uniform composition. If the composition of the examples that got that far are uniform, then that is good. Okay? And if not, we would like to add another test to help split it up, hopefully to purify it into, something that distinguishes between the two possible classes. Any questions? Okay. So logic, again, this idea of using decision trees I find appealing. The idea of being able to ask a feature, specify features, okay, and build a chain of logic that says, I'm going to decide you are the winner if this is true, and this is true, and this is not true, okay? Seems like a reasonable thing. And I don't think I'm going to make you go around with these examples, but it should be clear. Pick one of these at random. Somebody pick one. Snow on Christmas, okay? So is there any kind of, if we wanted to make a decision as to whether there's going to be snow on Christmas, is there some kind of a chain of logic that might be used to make a decision like that?
Yes.
What would be an example?
Temperature on the day.
Is there a high pressure? If the pressure is high, a little bit away from me, right? And if the chain is low, and if it is not warm, then maybe we've got snow, right? And the chances we will have snow. Does everybody kind of get the idea of that? So it should be clear that on any, you should be able to, on any kind of a world, build typically explanatory models that you can understand. Often there are, when you're making decisions, you're making them. The way I think about it is, in a decision tree, you are making a decision on the basis of, if this is true and that's not true and that's true, then this is what I'm going to decide. On a linear regression, you're saying, I'm giving you a few points for this and a few points for that and a few points for that and a few points for that, and then let's see how many points you have. Okay? So there's a different kind of underpinning to what's making the model. Any questions? Yeah.
Are you going to tell us what kinds of functions this doesn't work for?
Well, what doesn't this work for? This is a fairly rich thing, and I don't know if I can really tell you a class of things which it doesn't work for.
Yeah, I'm thinking if we work in two-dimensional space, right, you could definitely classify anything based on this.
With anything, so basically, I don't think that there's a systematic class of things that this is going to do badly at. Okay, that's, I guess, the thing. So what are the advantages of decision trees? One is, as we've said, they are nonlinear. One is that they naturally support categorical variables. Okay, if you wanted to say, did someone survive the Titanic, if more or less likely because their hair was red, it becomes a test, right? And there's no reason why your tests can't be categorical variables. So that's good. It's interpretable. One problem with a single decision tree is that it gives you only one path, basically, to survive, to decide. If if one of these factors was off, it immediately throws you into a different end of the tree, and you might end up with a different decision. You can make decision trees robust, as we talk about, by constructing many of them and then voting, and that's something we'll talk about a little bit later. The other thing is that you can use decision trees for regression. If you wanted to figure out what was the life expectancy of someone on the Titanic, okay, recognize that if they died on the ship, their life expectancy was probably about measured in an hour or two, right? But if they survived, it was much longer. You could imagine now taking all these examples and taking whatever data you had on them, and if you wanted to build a model for predicting their life expectancy, it would, you could build a different model on each one of these classes, on all the examples that made it to that class. And in that case, it would be a much better model of life expectancy, right? Once we remove the fact that people didn't survive the boat, then we could come up with a more accurate model for just that class of people. Okay, and that's part of the idea of these decision trees. Any questions?
So, like if we have just a simple linear function, increasing function, like for linear regression we use.
Yeah.
How can we use this classification and regression tree card to predict the values for like y, for simple x? Like
So if you want to predict y as a function of x, and you've got x has several features to it, one possibility is you classify them sort of like a little bit with clustering. You could view one of these trees as being like clustering. Does everybody kind of think that all the elements that make it to this point in the tree are all the same in some way, right? Namely, they're all young men or old men. Is that right? And if they're old men, then maybe now if you wanted to predict some other property of them, okay, building a linear regression on the people that are all past this test, okay, you can now have the opportunity to build multiple different regression models, and the characteristics of these people are quite different than the characteristics of those people. And so maybe by building multiple regression models, that would be better than building one regression model.
Like if we simply have y equal to 2x, suppose y equal to 2x, like simple line.
Yeah.
So like how will we do it using
Well, if you only have one variable, then there isn't much you can do. Notice here, this tree used 3 variables, okay, and there may have been other variables that were built on it. If you only have one input variable, there's not much you can do, and maybe that's another argument for linear regression. Can you implement an exclusive OR with one variable? No, so all the complexity of things goes away when you've got one variable. The interesting thing is when you've got multiple different variables. Okay, yeah? Okay, when we go into construction, let's talk about that when we talk about how we construct these things. Okay? If you talk about in general, these decision tree methods work very well. The biggest disadvantage that I have is almost a cultural disadvantage. Okay? I like linear regression because linear regression has this math, and they talk about convex functions, and it looks like you know something when you're talking about this. Does everybody agree with that? Okay? These decision trees seem to be are very much hacker-type things, especially when we start talking about the design of how you construct them. There is a lot less theory. There seemingly should be a lot less power as a result. In general, decision trees seem to do very, very well, despite the fact that machine learning people are probably rooting against them. Okay? And, but that's something to keep in mind. Okay, how do we build a decision tree? And there are many different algorithms for building decision trees. Let's talk about the simplest approach first. Okay? The simplest way would be that we're going to build it in a top-down manner. We're going to say, what's the root? The root is going to be our first test. We would like to find a single feature or dimension and a test that's going to split our elements into two different groups. what properties do we want those groups to have? Okay, if I have a test where I do a test and I split it into this group and this group, what properties do we want the subgroups to have? What?
Different, like they should be like yes or no, like the output should be different for both of them.
Well, you say the output should be different. What we would say is here we've got elements from class 1, a certain number of items from class 1, and a certain number of items from class 2, right? We would like on this node the number of items of one class to be much greater than the class on the other, right? And we'd like on the other side C2 to be greater than C1, right? We would like there to be some purification done by class. That would be a good test. Okay? What's the purest that we could hope to make a node? Entirely of one class. Does everybody see that? Can we always make it so that one of the classes is completely pure? At the leaf node is, suppose I have one dimension here, and it's got, let's say this is, my dimension x. Okay, and these are the values of my x things. Those are the positive ones, and these are the negative ones. Those are the negative ones, these were the positive ones. Is it possible to do a split to make that perfectly pure? Yes. How would I do it? Oh, okay, you're saying split that way. No, this is I need to have an x greater, is a threshold where x is greater than that. Okay? Is there a way I can split it so that the class, one side becomes pure? The answer is obviously yes. What if I go to the last example? Does everybody see that if I say that if x is greater than t, that then one side is 100% yes, I can say this is a negative class, right? So that's purity. What's the downside of that? Oh. Well, the other side is, is all mixed. So that's one downside. The other thing is that I have done very little work, I guess is one way to put it. On one level, this is a very, very pure thing. On the other hand, if I had a test and picked off one example, that's done relatively little work. Does everybody see that? So ideally, recognize that there is a tension that we would want in terms of trying to decide what our splitter is, what is our single feature that we would like to have. We want it to produce pure splits, but we also want it to produce balanced splits. Does everybody see that? Partially because this does nothing, and it would cause a big, huge tree. Part of that is also it's overfitting. Do we really believe that that test here is very meaningful? And the answer is probably not. Okay? So there's kind of a trade-off between the speed, which is kind of governed by the height of the tree, and the robustness here. Okay? We would rather make a test in the middle in the hopes that something good's going to happen. Okay? So how are we going to do this? We said that the simplest kind of tree building procedure would be a a greedy thing, where if we've determined that we are going to split, let's make it a little bit better. Let's add a couple more positive examples here. Okay? Where if we if we pick a particular threshold, how can we decide whether it's good or not? Okay? And we need a way to score how much confusion of classes there is. Okay? And a classic measure of confusion among classes is something called entropy. What is the entropy? Suppose we have a certain set of here m possible outcomes. So here we say there are m classes. Generally speaking, usually m is equal to 2. Okay, if we had a binary classifier, m was equal to 2. The entropy is minus the sum, as we sum over all possible classes, of for each class, the probability, the fraction of the elements in class I times the log of the fraction of the elements in class I. Now, what does this mean? If it's a fraction of elements in class I, what is the value of that fraction? It is between 0 and 1. Does everybody see that? What is the value of the log of something between 0 and 1? It is negative. That's why we have this negative sign, to make that kind of go away. So the entropy is going to be a positive value. And what does this kind of mean? Let's look at particular extreme cases. If we had complete disorder in our node, half of the elements would be in class 1 and half the elements would be in class 2. Does everybody agree? What would that work out to? That would mean that f of I is 1/2. This would be what? 1/2 plus the log of 1/2 plus 1/2 times the log of 1/2. What is the log of 1/2? Okay, it's minus the log of 2. Does everybody see that? And so summing up 2 times the log, 2 times 1/2 the log of 2, basically if there is complete order, the fraction in each class is 1 over the number of classes, and the entropy turns out to be log m. What if there was perfect order? If there was perfect order, okay, then one of the classes would have 1, and it would be 1 times log of 1. What is the log of 1?
0.
So 1 times 0 is 0, and everything else would be 0 log 0. What's 0 times anything? 0. The entropy here would be 0 if there was a perfect partition between the classes. Any questions? So entropy is a good statistic for measuring how much confusion there is, or equivalently how much information. If you study information theory, this is where this equation comes from. Any questions? And so if you think of entropy as information, you get all kinds of interesting, weird things. Like, which is going to have more entropy? A coin toss or complete knowledge? Okay? A coin toss, right? So if you use this to measure the information content of something, it's interesting that if you take a look at what TV show has the most information in it, it's the one that consists of random noise, right? Just a test pattern and stuff like that. If you really have random noise. Again, you guys now grew up in an era of cable. Has anyone ever seen broadcast channels where all you saw was that fuzz? That was the most informative thing on television, if you believed in information theory. Because, again, you couldn't predict what was in the image at any point, right? And, again, a coin flip means you can't predict it. Okay, that's high entropy. When you have perfect prediction, there's no information in it, right? Any questions about that? Okay, good. So once we have this idea of entropy, now what is our desire of how good a split is? When we do the entropy would measure how good each subset is. Does everybody kind of get that idea? We want a low entropy subset. Okay? We would want the split in such a way. What would be a way to measure what the split is? One measure is information gain. If we took the entropy of the thing on top, that's the entire set, and we subtract off the sum of, for each of the left and right children, okay, what was the entropy of that side times the size of that side. Recognize we want the entropy to be low. If we did this perfect split where one item came off, the entropy on that side would be extremely low, but we would only get credit for classifying a very small number of items right on that side. Does everybody see that? This is the size of the subset. This is the entropy of that subset. Generally speaking, we want big subsets, each with low entropy. Okay? And so the information gain is a measure that will do that. Any questions about that? Okay? There are other criteria which will measure the purity of a split, okay? But again, the basic point is you would like it to be some measure that rewards you for having pure things and rewards you for having large things. And the information gain criteria will do that. Any questions? So now you could imagine building a tree where you start from the root, you pick a dimension to split on, you try all possible thresholds and find the one that will provide the most information gain and make that the root. Does everybody see that? And then you can recur on each side. And that is a perfect thing to do. Any questions? So the good thing is you can build decision trees by greedy means, and it's a relatively natural thing to do. The bad thing to note is that sometimes the greedy tree isn't going to be, isn't going to be able to recognize what you want. If you think back to our exclusive OR case, what is the right split that we would want, okay, in this case, in order to be the root? We saw that the root we wanted was one that split down here or equivalently split across there. Does everybody see that? But if you look at this case, any rotation, any plane through the, through the origin is probably going to take half of the, have half the elements on each one. Does everybody see that? So it's impossible to tell that this or this is a better splitter than any, line through the origin. Does everybody kind of see that? You could kind of imagine that if you picked it by this criteria, it's very unlikely you would actually pick the one that we want as the root. You might very well cut through the blue points in half, okay? And, so therefore, recognize that the virtue of a particular split might not be immediately obvious, okay? Which is an argument that building this greedily is not going to find the best possible tree. Any questions about that? Is that clear? That I think should be clear. The other issue that should be clear is that you don't, you could, one way, what is the criteria under which you stop splitting? Okay? You could stop splitting once you have a perfectly pure environment where all these elements belong to the same class. In general, if we keep recurring, you will eventually get to a point where every element is pure, even if it's an element that stands alone. Does everybody see that? The trouble is that, that in general, if you build a tree where you're going to end up with, if you have n training examples and you're going to put a total of n leaves on the thing, almost certainly you are overfitting the data. Does everybody kind of get that idea? So there's kind of a trade-off here between overfitting and generalizing and things like that. In principle, you would probably not want to stop when the information gain is 0, but when the information gain is sufficiently small that there's no good further way to partition it. Any questions? There's other ideas that go and build the full tree and then figure out what should you prune away later. Let's say you want to find what's the best tree that has 17 nodes in it. You build the full decision tree, which would have n nodes in it. And then maybe you go back and prune out the subtrees that look like they're least valuable. Okay? And, so bottom line is that there's a lot of what I will call hacking in decision trees, more so than I would say is science. These are all logical considerations. Exactly why one is better than the other seems to be a thing you test experimentally more than with theory. Any questions? Okay, good. The other idea for decision trees that turns out to be a very important one is that there's no reason why you can't make more than one. Does everybody kind of see that you started at the root by making a first test? What did we do for the first one? Let's say we have 20 features in our data set. A reasonable first thing is we picked one of them and said, okay, the thing is age. Okay, if age is greater than this, say yes. We could have started our decision with a different feature. Does everybody kind of get that idea? And if we had started from a different feature, it would lead to a wildly different decomposition. So we can imagine a world where we build multiple different decision trees by at each step randomly picking a feature and finding the best way to divide on that. Does everybody kind of get that idea?
So instead of greedily selecting which decision results in the most information gain, you would sort of a priori choose a feature and then build the tree based on the same principles of information gain, but starting from those selected routes?
Well, what I would say is that originally, if we thought about the greedy algorithm before, maybe you could imagine my greedy algorithm is for over all features, try all possible thresholds, and give me the one that gave me the maximum information gain. That's probably what the greedy one would have done before. Now let's say instead, randomly pick a feature, and then set the best possible threshold by information gain. You don't want to make completely dumb decisions. But if we're going to decide to classify it based on this feature, let's find the best place where we could. So information gain will let us set the threshold. But if we allow ourselves to randomly pick which feature we are using at each level, we can come up with a zillion different decision trees. And generally speaking, it's not obvious that one is that much better than the other. Does everybody see it? It should be clear that they are different. Okay? You could imagine a world where, what would be a different tree if we had been looking at the Titanic example? Did I have the Titanic one? Maybe if we first looked at it according to, are the number of siblings greater than 2.5? Okay, if we checked according to siblings, maybe we found that people who didn't have any brothers or sisters were the ones that didn't make it. Okay, whether they were male, whether they were female. Does everybody see that if we had made this decision first, we would have ended up with a different logic? Okay? And again, the idea here is we can now build a, a variety of different classifiers. And this gives us many, many different advantages if we have a lot of different decision trees, classifiers trying to do the job on our data set. One is we could use some kind of voting procedure to try to decide which is. So let's say I had 100 different classifiers that were going to try to predict whether you were going to survive the Titanic. Okay? If 50 of them, if more than 51 of them say that you're going to survive, we say that you survive. And if 49 of them say you didn't survive, well, we wrote you off as dead. Does everybody agree? So we could use voting for this. Voting would enable us to presumably increase the robustness. We're not making our decision based on one particular chain of logic or one particular thing, but a large number of chains of logic. It's also true that this enables us that having multiple trees gives us an idea to judge our confidence in a classification. Suppose I build 100 decision trees for survive or dead, and you come up surviving in 98 of them. Are you feeling confident?
Yes.
You're feeling confident, right? If this person is dying in, 37 of them, is surviving in 37 of them, do you feel confident? You don't feel confident, but do you feel hopeless? No. You realize that you're on the borderline here, and if you push somebody else off the boat, you might be able to make it, right? Does everybody kind of get that idea? It should be clear that you can use the voting, the degree to which these principally independent classifiers agree with each other gives us some measure of how confident we are in our decision. Any questions about that? That should be an obvious win. Okay? There's other different engineering ideas that people use to construct multiple trees. Maybe you really liked using a greedy algorithm where you picked always the best possible splitter. Okay? Well, one way that you might generalize that idea to multiple trees is what if I took, instead of all the passengers on the boat, I picked a random subset of 100 of them, and then ask you to build the best possible classifier on these 100. Likely this tells you something about the fate of the others. But now suppose I throw those people, back in the mix and now pick another subset of 100. Does everybody agree? I'm going to be learning different trees here. They have some degree of correlation among them, but not, depending upon how big the data set is. Okay? And the claim is that this technique, which is called bagging, gives me an alternate way. Instead of picking subsets, my features randomly. Here I pick my test cases randomly. Okay? And again, I can construct an ensemble of different votes and do that.
How is it different than training? Is it just that we repeat it over and over again?
Well, in the training, instead of building one tree, we're going to build 1,000,000 trees, or 100 trees, or something like that. Right? And we could have them, the randomness either incorporate which features we pick, or the randomness incorporate which examples we put into the data set that time. Any question about it? Okay.
You also use like subsets of features, like subsetting rows, also subsetting of columns. Like we just pick only 3 columns for building a tree, or then 5 or then 7 to build variants.
An alternate idea that you're proposing now would be segregate the features so that these trees can only use this logic, and these can only use these features. And that may be a good thing to do. Okay. Again, this is why I would say this is a hacker's game. There's no reason why you couldn't go off and say, I can implement this and I can try it. My instinct is that it's hard to believe when you randomly do this that the hard partition of the features is a good thing. Okay? So you kind of like the ability to use all that you have. So my instinct is that it's less desirable. My instinct is that's less desirable because you're kind of limiting your choices of what might produce a good split. Okay? But again, if you don't believe me, you implement it, and there's no, I don't say that with any degree of firmness here. Any questions? Okay. Now when we have all of these different trees, now we get a kind of fundamental question that's going to lead us to another machine learning question. If we build 100 different decision trees, and we want to now combine their judgment to to decide what the next what the right class is, should we give each tree equal votes or not?
Not necessarily.
Not necessarily. Why would you not want to give them necessarily?
One might be more accurate than the other, so we can just do the weighted combination based on the accuracy of the weight.
Does everybody see that in the United States we allow everybody equal votes? Okay? And what did we end up with at the election? And is that a vote? Okay, so I'm not sure that's... So another possibility is you take all the people that I think are good, have good judgment, and give their votes more weight, right? And whether that's a better thing to do in democracy is unclear. But for classifiers, it might very well be a good idea. So how can we use multiple classifiers in a voting situation? Okay? The simplest thing is we could give each one gets a vote, and we take the majority label as our decision. Now, the real question is whether we should give each of the trees an equal vote, and it's not obvious that that's the case. Here is an example where, which I would like to use as kind of an illustrative example. Here we have 5 different classifiers, and these are my items, my instances, V1 through V5. Okay? And actually, wait, no, let me just put it this way. No. My classifiers are V1 through V5. My voters are A through E. Does everybody see that? The classifiers are V. V is for voter. Let's think about that. V is for voter. These are the items. Okay? And there's a star if it correctly classified that item. Does everybody see that? So what could we do? We could, if we look at it, this classifier got 80% right. This classifier got 60% right. This classifier got 60% right. So did these guys, also got 60% right. Does everybody see that? Now, if we take the majority label, okay, and we say which label was it that most people agreed on, okay, note that the majority classifier in this case was right only 60% of the time, okay, because those are the ones, if we took the ones that had multiple stars, they were right only 60% of the time. But if we gave these three classifiers, okay, weights of 1/3, 1/3, 1/3, and ignored the other two, in this case we get a classifier that the majority element will be right every single time. Does everybody kind of get that idea? So you can imagine a world where if we could try to, once we knew our had our different classifiers, if we assign them the proper weights, we can make better decisions than if we assign them uniform weights. Perhaps we would measure them by accuracy, but if you look at just by accuracy, there's no way to tell just based on accuracy that these two are better for us than these two. Does everybody get that idea? They're all 60% accurate. We could use some kind of linear regression, perhaps, to try to figure out the weights of these things. You could imagine a world where every classifier on each item gives a vote. Is it in class 1 or class 0? And so that the features would be what did each classifier vote on. And then you could imagine doing linear regression, and that would give you some way to find weights of these things. Yeah?
So, one thing I was thinking about sort of like rods and cones, like in your eye, like one's better at like discriminating between like colors, the other's better at like light percent. Can you sort of build classifiers that sort of are good for, are really specialized in certain things and combine them?
So you want to say build classifiers. What would be better is if we had classifiers that were good for specialized things. What was good about classifier number 2? It wasn't that it got 60% of the items right. It was that it got the 2 items right that everybody else found hard to do. Does everybody see that? Yes. So overall, its accuracy was not necessarily something to stand out on. But in fact, it did well on certain examples, okay, that otherwise were hard to do. So, in fact, the other way to weigh these things, that maybe you think of it as rods and cones, but the way that I think about it is, maybe there is a way that we can pick which classifier gets the hard cases right, okay? And that would be an example, a technique called boosting. Boosting is kind of a orthogonal idea to how we would combine classifiers than regression. In linear regression, we weigh each classifier and give it a weight and give more power to the classifier. What boosting is going to do is go along successively, classify and try to build more and more classifiers for the items. But it's going to give higher weights to the items that haven't been classified together accurately so far. Okay? So you kind of imagine that it's going to go along and build a classifier originally for all the examples. And it finds the best possible, let's say, single feature split that would classify these examples. Now, the ones that got classified accurately, these we're going to call a little bit less important. And the ones that it classified wrong, these we're going to call more important. And now we go and ask you to build a classifier on the new set. On the new set, you get more points for classifying the examples we've had trouble with, right? And so now we find the best possible classifier for this new set. Okay? And after this, some items will have been classified right, and some items will have been classified wrong. Does everybody see that? If we boost the value of the ones that got wrong, okay, and reduce the ones that got classified right, eventually it gets more and more valuable to classify the remaining item that was classified wrong all the time. And the classifier will work extra hard to get that right.
Are we saying that a classifier that got
we're going to boost. Okay, so what are we going to be doing? Okay, basically, what we're going to do is score a classifier based on the weight of the points that it classified correctly. Okay, so you can imagine that if we have a all points are positive or negative, and we identify. Let's just look at, maybe this is the example that I kind of like. Okay, maybe we first build a classifier here that says everything on this side is going to be positive. If we look at, let's just come back here. Let's say that we first chose which classifier did best. We said this one. Everything on this side is positive. Anything on this side is negative. Okay? After that, the ones that were misclassified were these points. These were positive points that got misclassified, right? In the next round, we classify these points as having, we find a way to give them more weight. Okay, with some algorithm we said originally each point was worth 1. Now maybe the ones that we misclassified are worth 3. Okay? Now, if I get 3 times as much credit for getting these right, my next classifier might very well be one that goes here. Does everybody see it? It says anything that on this side is positive. That's great. I get credit for these 3. And the credit I get for getting these 3 right is worth more than the credit I lose for getting these 3 wrong. Does everybody see that? But once I've done this now, which were misclassified at this point? Now these 3 are misclassified. Does everybody see that? And if I now boost the weight of these items and I try to find what is the best single split, perhaps then I will choose this split. Does everybody kind of get that idea? And by now taking as my final classification, I am going to have a